All right, so let me go full screen. Just move a couple things so it's easier to see for me. And then, all right. So we left off here with our electron configurations, and we were really focused on the core, but now we're going to start looking at trends and what this does as electrons come and go. All right, so everything is based on the number of valence electrons, right? The core ones don't move or do anything. So it's really how many and what valence electrons are coming and going that determine the chemical and the physical properties. All right, reminder, the valence electrons are just the S and the P blocks of the periodic table. The D elements you might see a little bit in Chem, but not really. Those are kind of higher chemistry classes, so very small portion or possibly no one in the class. All right, we did the quantum mechanics, the numbers, we scratched the surface of quantum mechanics. And since it's due to S and P, there's 2 electrons in S and 6 in P. Basically, what that tells us is that everything really is focused on 8 valence electrons. So if you have a combination that gives you 8, you get something that's completely unreactive, which was on with no charge, no electrons coming or moving. That was the noble gases. And if you've been, at usually it's a kid's birthday party, but if you take a helium balloon and open it and breathe it in and out, right, you don't choke to death. It changes the sound of your voice. That's why people do it. But the point of it is you breathe it in and out just like you breathe in nitrogen gas, which we'll get to coming up. But they're both extremely stable and unreactive. All right, so since the noble gases are really stable and unreactive, the opposite of that is true. Things that either have 1 more or 1 less electron are then pretty reactive. And this is true for the halogens, which you don't have much experience with because they're so reactive that you never find elemental halogens anywhere on Earth. They have to be made by a chemical company, which we'll go through the process of how to make those in Chem 162. But the metals you do have experience with, right? Lithium is what's used in most of our fancy electronics these days, in phones and batteries, right? And if you've ever had a battery die on you in a phone or a laptop, it's hard to get a new one, especially shipped to Hawaii. And if you just YouTube lithium battery explosions, lithium is so reactive. It's not like your car keys are a nail. It's a different metal, and it has to do with what group it's in. Also, the higher up in the periodic table, the more reactive it is. So lithium is the first metal, highest in group 1. But the rest of them are reactive. It's just things are more reactive the higher they are up in the table. And the reason for that is due to those the number of orbitals is the core, there's a larger core electrons shielding the effects further down in the periodic table. The further you are up in the periodic table, the closer the electron is to the nucleus and the more dramatic the reactivity. Okay, so we already knew when we did the formulas the charges for these things, right? In general, metals were pretty strict, right? Group 1 is +1, group 2 is +2, right? 7 was -1, group 6 was -2, and then the elements in the middle got softer. And we didn't even discuss carbon because in theory it can be from +4 to -4, and that's again why you can spend a whole year on organic chemistry. It's all carbon based. So here's sort of a mix of these, right? Notice 4 carbon and silicone are left out, right? Metals are always either neutral or positive then, and then the opposite. And this is basically this idea that it's easier to get rid of one or two, even up to 3 electrons than it is for, say, the other elements on this side to get rid of 5 or 6 or 7 electrons, right? The elements over on the far right side, it's easier to grab an electron. So everything in group 7 is going to grab 1 electron, and then it will have the same number of electrons as the noble gas next to it, right? Then group 6, right, grab 2 electrons, then you'll have the same electron count as the noble gas in the same period or row. The reason this part of the periodic table here, where I'm moving the cursor, these elements are sort of left out here, is because this is that staircase of metals to the left and non-metals to the right. And these elements in between are halfway between a metal and a non-metal. And so they have sort of different properties. And those are all the ones that get used for electronics, right? So carbon is left out again because it's really complicated. And we'll see the beginnings of it in the next 2 chapters. Okay, so I put one of these ahead on the test to see who would get it. Oh, sorry, Ben. Why is beryllium left out? So these elements high up here act kind of strange. Lithium acts strange also. You'll see lithium in organic chemistry where it can form a bond with carbon, and lithium on its own is just peculiar. But it also does this great thing that we use it for in batteries. Beryllium just doesn't get a lot of use. Here's the thing with lithium is there's a ton of it in the Earth's crust, so it can be used pretty readily. Beryllium doesn't do much else. So, some of this is left in here and left out due to how much you'll use it in the future, how much you'll see it, and then how useful it is. So above aluminum here is boron, and boron does get used in organic chemistry and whatnot, but the normal person doesn't have much interaction with boron, whereas everybody's held, a soda can in their hand or aluminum boats, and we'll cover this too coming up. Same with lithium. Is the reason these things are expensive, lithium batteries, and we recycle aluminum cans, is they don't come out of the ground like you've seen, miners where they mine for gold and they find a gold nugget. They're in the Earth's crust like salt in the ocean is, and so they come out charged like this, right? Lithium and aluminum are both found in the ground, all the same with these groups 1 and 2 elements. And so the way you can get them as a metal is you have to pump electrons in, which means electricity. So like aluminum here is, I think it's the 3rd or 4th most abundant element on Earth. And it's like, besides iron, it's like the 2nd or 3rd most abundant element in the Earth's crust. So we recycle it because it costs money to pump those 3 electrons in, not because it's hard to find, right? Things are usually expensive because they're either hard to make or hard to find. And so electronically, lithium and aluminum cost money to make. So, but good question. And we'll see beryllium on a couple of examples, but it's such a rare element. It doesn't have a lot of uses like lithium does. So you just won't see it as often. And they left out a few other elements, and either due to them being rare or not having many applications. Right? Over here, like group 2 and 3, right? Sodium and magnesium, calcium. These things are used in proteins, and you need them in food, and people take these as supplements, right? Our bones are made of calcium, that kind of thing. And this is the kind of calcium you want, right? You don't eat pieces of calcium metal. It's really reactive. You have calcium ions. Okay, so what's the difference here is the valence electrons are the ones that come and go. So our ground state configuration, this one's sulfur, it's in the P block, 4th element over. So if it's a -2, electrons are negatively charged. Well, hold on a second. I live kind of near a fire station. Kind of gone now. So adding 2 electrons, they're going to go into those p orbitals and fill it up completely. And then cations are going to do just the opposite, right? The valence electrons are the outermost, so those electrons are going to leave. Magnesium, for example, the last 2 electrons are in the 3rd row, the s block, and there's 2 of them. So those are the 2 that are going to come out. Keep in mind, it's been a while, but these 1, 2, 3, 4, 5, etc. Are like rings around a tree, or layers of an onion, or think of like an apple where the valence electrons are the skin. You have to break the skin before you can get to the core. And so these are the electrons, the outermost S and P, that come and go. Okay, so this is a little foreshadowing here. You don't really know what these words are yet. Van der Waals is interactions between atoms where they're not actually bonding, which won't really make sense till we get to the next chapter. Covalent radius is 2 atoms that are directly bonded, connected to one another. We draw to mimic them. We show an atom with a line or like a rope or a stick connecting the 2 balls. And so the size of an atom, right, just like anything that's spherical, you measure it by the radius. So the atomic radius is an average radius of an atom based on measuring large numbers of elements. So when an element bonds to another one, it's the combined of the 2. And if you just take, huge numbers of these, you get an average. And that's where these numbers come from. Okay, so there's a couple of trends. The radius increases as you go down the group. And this is, again, just thinking kind of like planets going around the sun, right? The electrons are kind of like the planets. And as you get further away from the sun being the nucleus, the distance is greater. And we know this by, or, depends on how into astrology and whatnot you are, the solar system and whatnot, but the planets take longer to go around the sun, and that's a reflective of the distance. All right, that one's kind of the easy trend. The atomic radius decreases as you go across the period. This one's not as dramatic, but it is there. And the idea here is that the electrons, as you move across, they're going into this orbit that's the same shell and thus the same distance. But as you go across the table from one element over to the next, you get an extra proton, right? Each element is another proton. And so what you have is a larger and larger positive charge at the nucleus, but the electrons are the same distance away. And so you get, it's a decrease, but the typical term is called a contraction. So that is a decrease in the behavior, which is atomic radius here. All right, so here's one of these, pictures, right? 2 atoms next to each other, and they measure the distance, and then half of it is then the radius. Here's bromine, and we'll get into its bonding, but it's a covalent chemical bond, and so then they just take it and divide by 2, right? And so I think everybody, it's a science class, knows what a radius is. All right, effective nuclear charge is what I was describing there, where you have the protons at the nucleus, and the core electrons will essentially cancel out some of the positive charge, but then those electrons are going to feel the charge, the difference between those. Right, and this feature is called shielding, where the core electrons shield the outer electrons from the full strength, and you get an effective charge. This has to be positive. And we'll see a couple of examples coming up here. All right, so remember, Z is just the number of protons. This is their little way of labeling and stuff. So S is the electrons. In lower energy levels means the core. And we'll remember the labels here, S, P, D, and F. And so the effective charge is then the total number of protons minus the core electrons. And this is just showing you the math behind it. I won't be putting one of these on the test. It's just so you understand the trend that's going on. So let's pick the simplest possible example for this. Lithium has 3 electrons and 3 protons. The 3 protons are in the nucleus. Now we know the electrons are circling around in these orbits. The first 2 are in the S, and that would be our core. Then this 1 electron is out here in the next orbit. So we have 3 for the number of protons. 2 of the electrons, the core ones, are doing the shielding. And so this single electron feels really just a +1 charge. All right, this is just doing the transition metals, which I'm not putting the trends on here, really. I think this is a little excessive. The size increases as you go down, just like it does for all of them, right? That's planets further away from the sun. The atomic radii of the transition metals is roughly the same size across the D block. So remember the d orbitals are those weird 4-lobed kind of confusing ones, and so the trend is a little bit different as the orbitals get more complex, and so you don't see as much of a difference in the size. Then less difference than across the main group. Again, that's the orbitals. The valence shell, the NS2. Remember, that's our valence is the S and P. So the d electrons, they're not really our valence ones, and that's why we left them out, right? The valence ones was S and P, so 2 + 6. And then the effective nuclear charge on those NS2 electrons then is basically the same. Because then you consider the d electrons canceling each valence electron that's added in. So this is why the transition metals are basically the same within the group, or within the period or the row, I mean. So here's a plot of these to give you a better feel for it, right? So hydrogen, and then now that you have an extra proton pulling on the electrons, we see a little contraction, right? It's smaller. But notice here, then when you go to the next element, it shoots up and it's way bigger. Right, because this would be Mars, and then lithium would be Venus, planets around the sun. Okay, then as we move across, you get more protons, so the effective charge builds, and our core electrons is just these 2, so it can't shield it, right? We'll explain this little dip here later. Then we get to the noble gas, and we move out to the next orbital, right? And then it slowly contracts as we go across. And then we see the transition ones are complex by those, the d orbitals. And we see that the trend is less and less as we move further out from the periodic table. And that's because the core electrons builds up, right? Helium at first, then neon, then argon, etc. And the core blocks these charged effects more and more as we move across. So for us, the important part is really we're only going to compare elements that are in the same group up and down, because the trend stays predictable. All right, so here's the general trend. The most important one is the radius increases as you go down, right? And decreases as you go across, but the more important one is going down, it gets bigger. All right, so in order to ask a fair question, you have to do something that stays within the trend, right? So we have a trend for going over and down, which means if you're asked to compare two in a period, you know the trend, that makes sense. If you're asked to compare two in a group, you know the trend, that makes sense. If you're asked to compare two that go against the trend, which we see here, then it's hard to predict. Right, so for these two, for example, right, as you go across, it should decrease, but as you go down, it should increase. So which one's bigger? It goes against our trends. You would need that table to look it up. So you won't see one where it goes against the trends. And, you know, honestly, like, this isn't the most important thing. So there'll be probably one problem on the test with these trends, these things we're covering in here. So here it's just going through and giving a couple of examples, right? Remember the S for the transition metals are our valence electrons. So those are the ones that come out when you have an ion. You lose the S electrons first. All the transition metals don't have any P electrons. So for example, iron 2 and iron 3, you remove those S orbitals to get to both iron 2 and iron 3. And then now for iron 3, you can remove one of the D electrons. And it's doing the same thing here for copper. So there's copper metal. And this is a rare instance because it has the option where you could do 4s2 3d9, or like this, which is the appropriate way it's supposed to be, 4s1 3d10. It's a subtle distinction and kind of not completely beyond the scope of our class, but not really worth focusing on. You know, it's a higher chemistry thing. It's just foreshadowing it here. Okay. And we're covering all this stuff because it has applications to different things here and there. And this is one where the application actually should become of interest to everybody, regardless of what your major interest, etc. is. So you can see the two key words here in bold, paramagnetism and diamagnetism. It just means unpaired electron. And diamagnetic means that they're paired up. There isn't a single electron by itself. So things that are diamagnetic versus paramagnetic have different electronic properties. And if you've ever heard of, say, an MRI, or maybe some of you have had an MRI, basically the way an MRI works is it looks at elements that have unpaired electrons. And things that have paired electrons are silent. So you can image chemicals or, you know, biological tissue, and the things that are paramagnets show up, the things that are diamagnets don't. Here it's giving an example of zinc. So zinc metal is both diatomic, and zinc 2+ is both diatomic, because the electrons that come out of the s orbitals. They don't come out of the d. If they came out of the d, then you would have two of those orbitals being unpaired, but that's not what we see. So if some of the trends that we see, some of the things that they're telling you, is because we have electronic ways of looking at these, and they're, you know, for this example, they're both silent. You can't see them in these machines, which means that those electrons must be coming out of these s instead of d orbitals. All right, so you know, there'll probably be one of these on the exam, the next midterm. Write the electron configuration, determine whether iron and iron 3 are diamagnetic or paramagnetic. All right, so go find iron on the periodic table. 26th element. The noble gas before it is argon. We've got 18 electrons. We don't need to worry about the core. They don't do anything. We move across till we get to iron. 4s2 and 3d6. So clearly we've got unpaired electrons, right? And then here's a little animation. If we go from iron, the atom, to iron 3+ the ion, the electrons come out of the 4s first, but that still doesn't change the fact that we got these unpaired electrons. And then now, instead of 4 unpaired, we have 5 unpaired. So with these things like MRI and other ways for looking, if you've ever had a family member that had cancer, some of the ways they look at these is by this paramagnetic features. And the more unpaired electrons you have, the higher the intensity of the signal. And so things like this, and we'll see the f orbitals, the f elements, some of those can have 7 unpaired electrons. And it sort of tells you, it's that atom or ion then will be glowing 7 times the intensity of something that only has 1 unpaired electron. Okay, so we've covered here what ions are. We covered the radius trends for the elements. And now there's a little bit of trends for the ions. So if the ions are in the same group, then they have the same charge. The obvious one is that the size increases as you go down the group. That's the same, Mars, Venus, Earth, Mercury, Venus, Earth, Mars, Jupiter, etc., right? As you move down. The key point here on this slide is cations versus anions. What happens? Well, you're adding or taking electrons away, but the number of protons stay the same. So cations are going to be smaller because those outermost electrons are now gone. And then anions are going to be bigger because you've added in electrons, but the number of protons hasn't changed, right? And the protons are positively charged and they're pulling the electrons towards it, but the same power, the same Z effective is there, but now there's more electrons, so it can't pull on all of them as strongly. And then there's little exceptions, and I don't put exceptions to the rule on here on exams. It's silly for an intro class. All right, so the larger that positive charge, the smaller the cation. So most of our cations were +1, +2, +3. So as the charge goes up, it's going to pull the electrons closer, and it's losing more electrons from further out. ISO, just in case you don't know, ISO means the same in the world of science. And electronic means number of electrons. So isoelectronic species means something that has the same number of electrons, and thus same electron configuration. So just like with the larger the positive, the larger the negative, the larger the anion. Then here, it just gives you some actual measured values. We're not gonna need these values. It's just showing you some of them. And a little misleading here for group 4, because this could be +4, -4, depending on what you're doing, right? And then, carbon's a non-metal, but way down here at the bottom, lead is a metal. And so look how even the way the book is associating it is -4 here, but then lead down here, since it's a metal, is never minus. Its 2 common states are +2 and +4. Okay, so here's that trend, right? Group 1, we're losing that electron, and it's more dramatic the higher up, because the protons and the electrons at play are closer to the nucleus. And so that electron that you're moving is in that outermost orbital, and with it gone, you go back to the core from the noble gas before. Right, then as you move across the table, the charge goes up, and so the contraction should be more dramatic, right? So 95 here, versus 65 versus 50. These are PM. P is pico, and that's smaller than nano. That's 1 × 10 to the minus 12 meters. But it doesn't really matter what the unit is, right? We're just looking at the trends and the relative amounts. All right, then the anions are going to do the same. Right, the size always gets bigger as you go down for everything we covered. But now here, right, is the element neutral on its own. But now if you're adding in electrons, the nucleus, the charge stays the same, and it can't pull the electrons as close. And so you see this swelling of the atomic radius in the ions. And it's more dramatic for the larger the charge. So, oxygen's bigger than fluorine, sulfur's bigger than chlorine, the general trend. Ionization energy. What this is it's just the energy to remove an electron. So electrons are negatively charged. The atoms have protons, so they're positively charged. I'm sure at some point in your life, you've had two magnets that are stuck together. They don't magically come apart. And basically what this is saying, the ionization energy is when you pull two magnets apart, that takes energy, right? It doesn't happen on its own, so it's an endothermic process. They measure all this stuff in the gas state. We don't really care how they measure it. We're just looking at the trends, learning where the electrons are and how they move, and explain the way chemicals behave. So the IE with subscript 1 means the energy to remove the first electron. Then IE2 would be the energy to remove the second electron. All right, the second ionization energy is going to be harder because here you're pulling an electron off something that's positively charged, right? Before you were pulling the electron off something that was neutral. Now it's positively charged and it holds onto that electron, more than it did before, right? It's harder to remove the negative charge of the electron to something that's positive than something that's neutral. Okay, so with this, we see trends that are basically due to what we just talked about. So the ionization energy of the first electron decreases as you go down the group. And this makes sense. Huh, that was weird. I don't know when it stopped or muted me and did this restart. Okay, so what? Look at the picture. Here, this is where I wanted to get to. Okay, so the ionization energies, right? 0 here is where the nucleus is. So the ionization energy is the energy it takes to remove an electron. The protons are all here in the nucleus. So to take the first electron off hydrogen, this is the distance. So the attraction is stronger here. Then lithium, let's call this 40. Now it's 150. For sodium, it's, I don't know, 190. Potassium's up here at 230, etc. You see the trend. So the electron that you're removing is getting further and further away from the positive charge. And also the core number of electrons is building up that protects that outermost electron. So the ionization energy, go back to that slide. understanding the ionization trends is just a function of knowing what ionization energy means, and then knowing the trends in the radius, what they look like, where the electrons are. Here, the ionization energy increases as you go across the period. This is minor. It's much less dramatic because the contraction of the radius distance is, we saw, was much less as you move across the period. Up and down was when you jumped from orbit to orbit, and that was what I pointed out there when we went back to that slide that showed the values. Quantitatively, they're picometer estimates. So then here's that ionization energy plotted. And these trends here have to do with the electrons that are paired up, right? So, and hydrogen's weird on its own, but right, lithium, and it's, it's pretty close, but as you go down, it gets easier, right? Here's the energy. So lithium wants to get rid of the electron. It wants to be +1. And so it doesn't take as much energy, which means it's more reactive. Elements that, like the noble gases, are happy. They're unreactive. They don't want to gain electrons or lose electrons. And that's why the ionization energy for them is very high. It doesn't want to lose an electron. All right, then these little trends you see here has to do with the electrons pairing up, right? So lithium and then here beryllium, that's your S, and they're paired, so this one's a little higher. Then here, as you move across the p block, this is where they're in single unpaired paramagnetic orbitals, and then here it pairs up, right? And electrons are negatively charged, so when you pair two of them in the same orbital, they repel each other a little bit. And so that's why you see this general trend here where the energy drops. And that trend becomes less dramatic as you move across the table because the orbitals are getting further away, right? And then the green ones here, the d orbitals, have much more complex shapes, so we really don't care about these trends. And you won't see those in OChem anyway, so there's no point in us diving deep into the d orbitals. And notice the f orbitals aren't even included in here because they get so much further out from the nucleus anyway. So here are these values tabulated. And this is just, chart versus the graph that was on the last slide, but same information. Here it's just, numerically put on there. So if you wanted to look at the actual value. But we really just care about the trends in the radius. And then that correlates to the trends in the ionization energy. Right, so this one's just going to pick the trend here. And again, it's going to go with the trend, not against it. So we know that the radius shrinks. And we see that effect in the ionization energy. Same thing here, right? The radius gets bigger. That electron that you're removing is further away. Right, so here we have the, again, with both trends, and then here against both trends. So I'll never put anything on that's against the trends, because then you would have to go to that chart or table and look it up. I'm not going to have you compare numbers that you can just look up. It's silly. That's not learning. That's looking up stuff. There's little irregularities in here. And this has to do with that pairing. So when we covered the electrons, right, remember that electrons are negatively charged. So, for example, beryllium to boron, these two are paired, and so they repel each other a little bit. And this is why we saw that dip down in the energy to the boron. And then you see the same trend here in the p block where this electron here for oxygen that's now paired up, these two electrons repel each other because they're negatively charged and they're forced into the same orbital. So it's a little easier to pull this electron out, the energy versus the energy for just nitrogen above. These are subtle little trends. We saw them in the same spot on that plot. I'm not putting one of these on the test. It's just explaining with the electron configurations the trend that we saw there. So when you're breaking up that full sublevel, right, these two are unpaired, and so they repel each other a little bit. So it's there's a little bit of energy there. And here it's just showing, electron configuration from nitrogen to nitrogen plus and oxygen to oxygen plus. But again, a subtle little irregularity. I don't put strange things and really unique and exceptions and little irregularities on the exam. Okay, so this is just showing one last reminder of what we've already pointed out and that it wants you to know, right? Sodium is in group 1 on the periodic table. And so removing the first electron is easy, but then removing the second would be removing a core electron. This would be the equivalent of pulling an electron off the noble gas, the core electron. And the core electrons are really hard to remove, right? Because it's got your ion then has 8 electrons. It's happy and it doesn't want to remove it. So we see this huge gap when you go from removing a valence to then a core electron. So for magnesium, it's 1 over from sodium. The first ionization energies, first and second, right? That makes sense from the trends that we saw. Sodium wants to get rid of that 1 electron even more than magnesium. And then the second one takes a little more energy than the first. And then here's that huge gap where this is the 2 electrons that are valence, and then it's going to take 7 times whatever, I don't know, it's 5 or 6 times the energy to remove a core electron, which basically means it doesn't happen. It takes a ridiculous amount of energy. So core versus valence, and right here we saw that jump, right, times 5 ballpark, right? 3 to almost 12, so about 4 times as much, 1.4 to 7.7. Right, this one's more like almost 10 to 9 times as much. So to remove a core electron takes a huge jump in energy, which means it doesn't happen. All right, so that's removing an electron. What about adding an electron? It has a different name. It's called electron affinity. So affinity just means appeal, desire, alike for something. And so it's the same thing as before, just the opposite. So this is where something neutral is where we always started, gains an electron. Again, these things are measured in the gas state. In general, this is exothermic, but it could be endothermic, depends. There are situations. We'll see that electron affinity isn't as important. There's generally more energy released, but we'll see that this just isn't as important. And the reason for this is there are so much less elements that do this. It's only group 6 and 7 really that do this. But we see the same types of trends, just the opposite effect because the electrons being added instead of removed, as we saw before. But here the trends aren't. It's a little beyond our need and our what we need to do. But here are some of the values. I'm definitely not putting an electron affinity problem on the exam. You won't even really use this in OChem. It's even less important. Chem major people, and especially maybe physics and some nanotechnology engineering, electronics applications. This stuff is good to be aware of, but for the majority of us and the majority of people in the class, it's not really that relevant. Okay. So there's a little shifting gears here towards the end, where obviously you can tell from the slide, metallic character. So a big part of chemistry, freshman chemistry here, is supposed to take you from what you've already experienced and learn how things and why things behave on the atomic level. So the top check marks here are stuff you already already knew. So malleable just means you can make jewelry. You can bend metal and make shapes out of it, right? You've seen a copper pipe, piping in houses and bumpers and jewelry and stuff. Ductile means you can pull it into wires, pretty much the same meaning. But this is how they run, electricity works in a building, right? Is that there's electricity in the home, the power comes in and the wires go through the house, the walls, where you can't touch them so you don't get electrocuted, and then they go to the light sockets and fixtures and things like that. I'm assuming everyone's seen metal and that it's shiny and reflects things, right? Aluminum foil, the kind you buy at the grocery store, you can roll it out. And I lived in Seattle for a little while, where I had a friend that was from Alaska, and in the summertime, the sun comes up so early, and I wasn't used to that. I didn't grow up there. And the guy I knew from Alaska told me the trick that they do there is you just tape aluminum foil to your window so that it reflects the light out and you can sleep, to normal hours, and not, in Seattle, the sun came up like 4:30 or something in the morning. In June, it didn't go down until like 10, but Alaska, depending on how far north you go, you've got complete light and complete dark. Conduct heat and electricity. Again, you don't take your car keys or house keys and put them in a light socket. You don't touch a hot pot or pan. So it's sort of these beginning ones, you already knew that. What we're supposed to be doing here is learning about on the atomic level. So metals can form these oxides, and we talked about bases a little bit, and we'll do it more next chapter or next semester. Here we talked about ions, right? So like I pointed out there, and when Ben asked that about beryllium, we saw there that, and we talked about it, where lithium and aluminum and these things that come out of the ground as ions, right? Sodium is in the ocean, but it's sodium plus. It's not sodium metal like your car keys. Those ions are cationic because they're metals, they lost the electron. And they're either in the Earth's crust or then they're like this in the ocean, right? Sodium in the that's in the ocean. And how do they get there? They lose the electrons. If they have if they're in the metallic form, which is what we'll cover how a battery works in Chem 162. So all the aluminum and lithium on Earth already lost the electrons long before we came along, and it's in the Earth's crust. So we actually have to do the opposite when you want to make a lithium batteries. You get the lithium ions. And this is how they make sodium based batteries, is they take sodium out of the ocean and then they pump an electron in, and you can get sodium metal. So losing the electrons is called oxidation. And the next bullet coming up here, mostly all these things, right? Metals and non-metals kind of have yin and yang opposite behaviors. And so non-metals then gain electrons. And this is where chlorine, all those halogens, like in the ocean, you have sodium chloride. The sodium lost the electron. It got oxidized. The chlorine gained the electron. It's not chlorine Cl2, the gas. It's chloride Cl -1, the ion. Again, the top check marks here are things you already knew. Non-metals, brittle in the solid state. I'd say, like a piece of toast. Dull in the sense that they're not shiny, right? They don't reflect things. So think of things that aren't metals, a leaf, a tree, a shirt, all these things that don't have metals in them. They don't conduct heat or electricity. They don't. The only thing different here is, besides this, I don't really love this brittle in a solid state, is that they can be in multiple forms, right? Solid, liquid, and gas, especially like water, for example. Instead of conductors, they're insulators, right? So when you go to pull a pot or a pan off the stove or the oven, you go and you grab a pot holder that's obviously not made of metal, and the heat doesn't conduct through and burn your hand. Same thing, if you've ever done like electrical work, if you're into like, I don't know, remote control cards and stuff like that, this is one of the ways you don't get electrocuted, right? And you see this in old movies and cartoons, right? You don't plug a toaster in and throw it in the bathtub because you'll get electrocuted. And when electricians do things, you wear gloves and you don't touch the metal directly. Okay, then our last check marks here are the stuff that you're learning now that go along with the behavior non-metals, but not on the down to the atomic side, right? We saw some of the acids and the molecular shape of those, and we're going to get to the bondings. You needed to memorize the polyatomic ions, and then this we started to come up with here just this last chapter, right? That they gain electrons, and now we've looked and learned about where those electrons are orbital-wise. Metallic character increases as you go left, and we saw that on the periodic table, right? Since all the nonmetals were to the right, obviously things get more metallic as you go away from the nonmetals. And then increase as you go down. We really saw that in group 4, right? Carbon up at the top is a piece of charcoal. And then all the way at the bottom in the same group was lead. That's, if you've ever held a bullet, shot a gun, like a lot of pots and pans, really old ones are made out of lead. Right, and so they have aluminum here as gray as a metal, but right, you've held aluminum before, and like it's it is definitely it's metallic in nature, but it doesn't feel like a piece of lead, right? And again, carbon, right? This is your pencil lead or a piece of charcoal, and then all the way down to a bullet or a pot or a pan. That you cross over from a complete non-metal to a complete metal in these groups. 6, 7, I guess technically 8, but the problem as you get down here is 84 PO is polonium and it's radioactive. So in bismuth, you don't really see or use too much. But lead is a really common cheap metal, right? We've been using it as bullets in wars for hundreds of years, and no one goes around picking up the bullets. So they're obviously not worth that much. It's a pretty easy element to come by. It's an easy element to make into a solid piece of metal. And that same trend, as you move across, right, you can pan for gold. Here's gold, 79 AU, and copper, pennies are made out of copper. But these ones over here, further, lithium is reactive with water and even oxygen, right? And that's why you have them encapsulated in plastic inside a battery for your phone or your laptop or whatever high-tech device. And you don't want to puncture these. They catch on fire. So okay, then here in just a few slides, they show you a few examples of these with pictures, a little better than me talking about it, right? So they picked 5. I like 4 better, right? Because you've used a pencil lead and charcoal before. No one really uses bismuth, but nitrogen's a gas, and phosphorus is this reddish powder. Arsenic is kind of dangerous, so it doesn't really get used much. But as you move down, these things turn into, bismuth. Lead is right here next to bismuth. So Bismuth and lead are pretty similar. It's just there's a lot more lead than bismuth in the Earth's crust. And here, period 3, we're moving across the periodic table where, reactive metals that, sodium is just below lithium, catches on, creates a fire when it interacts with water, right? And then aluminum, we have aluminum cans, and silicones, what computer chips are made out of, and phosphorus is this red solid, sulfur is this green weird solid, and then chlorine's a gas, right? So you're becoming less metallic, obviously, from some reactive piece of metal all the way to losing electrons all the way to something that gains electrons as a gas. I won't put one of these where you predict which one is more metallic. I think this is pretty silly because it's obvious by the trend, the staircase, right? These are the metalloids, the non-metals are green, the metals are gray. So the further you are to the left, and the more metallic it is. So there won't be one of these on the tests, obviously not against opposing trends, but that one's a bit silly. Okay, so then these last few slides here for this chapter, they just summarize and go through the trends for each group. So alkali metals, that's group 1, right? They got bigger as we went down. The ionization energy went down because the electron you were pulling out was further and further from the nucleus, from the positive charge. They lose the electrons really easily, so they're really reactive. You never find these alone. You don't go panning for lithium or panning for sodium like you would, like people used to do where you pan for gold. They're in, like sodium in the ocean is sodium chloride. They're non-metals with salt, sodium chloride, soluble in water, right? That's the ocean. The electron affinity is not really that important because these things don't gain electrons, they lose them anyway. The melting points, not something you need to memorize, but you could see this in the periodic table that I emailed out and put on Laulima, because go back here. Fluorine and chlorine, for example, are gases, then bromine is a liquid, and then iodine is a solid, and those are color-coded on the periodic table that I put on Laulima. So obviously melting points decrease as you go down the column for everything, right? And so the density increases too, right? If you're a gas at the top and a solid at the bottom, obviously that's more dense. Then here just shows a table of all the data that we've covered, and here's where they're showing you when you throw these things in water, what they'll do is they'll create hydrogen gas, and then the heat from the reaction will ignite the hydrogen gas. So it just tabulates the radius, shows the configuration, the melting points, and then skips over to another, right, the halogens. So chlorine on down, same trend in radius, same trend in ionization energy. The electron affinities, now these are kind of relevant because the halogens want to gain electrons versus, there's not much said here about the ionization energies because they don't want to lose the electrons, they want to gain them. Again, just like those group 1 metals, you don't find these by themselves. You don't find chlorine gas in nature. It's too reactive, just like you don't find lithium, sodium metal, right? Table salts in the ocean, sodium chloride. You find these as salts either in the water or as salts in the earth, in our mind out of the earth. We haven't covered the reactivity with hydrogen yet. That's acids, that's next semester. Then the melting and boiling points and the density obviously should go down. And here they're showing you that chlorine, I know it looks like there's some on the bottom, but chlorine's a gas. The bromine is a liquid, and its boiling point is just somewhat near room temperature. So here's bromine, and you know, like water, for example, boils at 100 degrees. So Celsius room temperature would be 25. So it's, you know, half, or, you know, say room temperature was 30 degrees Celsius. That's about half of the boiling point. And so if you heated up water to 50 degrees Celsius, you would see some steam and vapor coming off it, right, when you boil water. And so that's what you see here. The iodine, same kind of thing. It's subliming here, right? And solids do have vapor pressures, right? If you like to cook in the kitchen, if you slice up onion or garlic, in order for you to smell it, or when you're baking cookies, there's some sugar in the air. Otherwise, you wouldn't be able to smell it. So the iodine is a solid, but you do see some vapor. And dry ice is what's known to do this the most dramatic, but it's much more dramatic than iodine is. This is fairly subtle. I won't put one of these on here. This is just kind of like explaining and combining things, right? So salt, this is an example of a classic salt, a metal group 1 and a non-metal group 2. And this is what we see that's, you know, like this is potassium bromide, but if it was sodium chloride, when you get out of the ocean and you don't rinse off at the showers, you can see table salt like on your arm hair, or dried on your skin. And you see, just like the table salt that you might buy and like to put on your food in the kitchen, at the dining room table, this is what is dried on your skin. Now, this is saying gas phase, but right, it's just aqueous in solution when you get out of the ocean. Here it's talking just, this is what we saw on that slide where you saw the sparks from rubidium as well, but lithium and sodium, and right, lithium, if you know, YouTube lithium batteries exploding, this is why the moisture that's in the air reacts with the exposed lithium metal. It grabs, it loses that electron, and then it reacts with water. That electron goes shooting off onto one of the hydrogens, the hydroxide, goes on, becomes negatively charged. Hydroxide is OH minus. You get hydrogen gas, and then hydrogen gas is flammable. Yeah, let's skip this. You'll see this a little bit in Chem 162, but I think this does more damage than good to cover the reaction of two halogens together. The noble gases do nothing, right? The radius increased as we went down. The ionization energy, right? It was huge, and it basically doesn't happen. That's why they're unreactive. But to get that electron off is going to be easier as you move down the column, because the electron you're pulling off is further and further away from the nucleus, from the positive charge. These are by themselves, they're monoatomic, they don't react. So the way that chemical or gas companies sell these is they just take air that we breathe and pump it down, and then they separate them by their boiling points. And they're all gases. So no trend. I mean, the boiling points, they're really low, and we see that trend in them, but you don't ever get to where one's a liquid or a solid. They're all gases, right? This is in Kelvin, so room temperature is 293. So even xenon, the highest one is, you know, 165, where room temp is 293. So no, you know, I don't know that that temperature ever even happens on Earth. Maybe Siberia or something like that. I don't know. And then we saw the behavior of gases, and we did looked at the density of the gases, right? So neon here is pretty close to the air we breathe. Neon is pretty close mass-wise, somewhere between neon and argon. This is, you know, the nitrogen, oxygen gas atmosphere that we breathe on Earth. So the other ones are heavier, and then this is why they use helium and blimps, is it's much lighter, like 0.18 versus, I don't know what, getting, a mixture of air, a mixture of oxygen, nitrogen, air is 1.2 or something. Okay, a touch early, a few minutes early, but obviously no need to go start a new chapter with only a few minutes. Hit this button. So hopefully the recording works out all right, the way it stopped kind of weird there in the middle of class. But if not, it seems like everybody was here today. I did lose a recording in my other class when the Zoom just closed down beyond my control. But anyway, that's all we'll cover for today, and then we'll pick up here at the next chapter, and we'll sort of shift gears and talk specifically about how chemicals are made and the atoms bond together. Instead of here, we were just talking about the electrons coming and going from the specific atoms. So I'll see you Wednesday, or feel free to unmute or chat box and ask, questions, comments, thoughts, feelings.
I might not see you Wednesday, but have a good day.
Cool, sounds good.
Thank you, Professor.
Yeah,
See you.
you're welcome.